In the last week, we introduced the notion of eigenvalues and eigenvectors of a linear operator on a vector space V. We also defined the analogous notions for an n cross n matrix. We thereafter defined what is the characteristic polynomial of an n cross n matrix A, and we observed that the roots of the characteristic polynomial turn out to be precisely the eigenvalues of the matrix A. We also use this to study the particular example of the Fibonacci rabbits. In this week, we extend further the study of eigenvalues and eigenvectors. We begin by recalling the definition of a characteristic polynomial. So, recall that for an n cross n matrix A, the characteristic polynomial of A is the polynomial given by determinant of A minus lambda I. So notice that this is a polynomial in lambda. So yeah, we'll come to that in a minute. Let's look at an example. What is it if it is some arbitrary 3 cross 3 matrix? A11, A12, A13, A21, A22, A23, and A31, A32, A33. Suppose some arbitrary 3 cross 3 matrix is given, then f of lambda. So let me just write it like this. So let f of lambda be the characteristic polynomial of A. I'll just in short, let me write it as CHAR, polynomial of A. What do we know about A of f? What do we know about f? Then f of lambda is just the determinant of this matrix A11 minus lambda, A12, A13, A22, A22 minus lambda, A23, A31, A32, A33 minus lambda. So if I am to write down the expression for the determinant using the cofactor expansion, this will just turn out to be A11 minus lambda into the first cofactor is A22, will be like this. Maybe I'll drop this and write it again. A22 minus lambda into A33 minus lambda minus A32 into A23, then minus A12 times A22 into A33 minus lambda minus A23 A31 plus A13 times A22 A32 minus A22 minus lambda into A31. So this is what the expression for the characteristic polynomial of A will turn out to be. If you notice carefully, I'll not expand it out any further. If you notice carefully, the polynomial of this particular polynomial is a polynomial of degree 3. Notice that f has degree 3. So observe that I am now using lambda instead of x for the indeterminate. It's the same. No confusion should come up because of that. All right. So maybe one more example would be to, so as you can see, the characteristic polynomial has a tendency to be quite messy. For example, if you look at higher n, or rather n greater than 3, the corresponding expression will be far more complex, and yeah, it has a tendency to be messy. However, in the particular case when our matrix is a diagonal matrix, the characteristic polynomial turns out to be particularly nice. So if So this is maybe another example. If capital A is something like say A11 0 0 A22 0 0 to ANN. Suppose this is our basically diag of A11 A22 up to ANN. Then what will be determinant of A minus lambda I? Let me write it in the compact form. This is going to be determinant of the diagonal matrix consisting of A11 minus lambda, A22 minus lambda, ANN minus lambda. This is just going to be the product of these entries, which will be A11 minus lambda into A22 minus lambda, ANN minus lambda. So yes, so diagonal matrices we can very easily compute the characteristic polynomial. Okay, now let's explore some more properties of the characteristic polynomial. So the characteristic polynomial has this particularly nice property that it is invariant under similarity. So let me write it down as a proposition and elaborate on it. So let A and B be similar matrices. So recall that A and B are similar if there exists a polynomial Q such that B is QA Q inverse. So let them be similar matrices. Then the characteristic polynomial of A is the same as the characteristic polynomial of B. The characteristic polynomial of A is the same as that of B. So let's give a proof of this and then discuss the implications of the proposition. So notice once more, the proposition tells us that the characteristic polynomial is invariant under the property of similarity. In other words, if you have two similar matrices, the characteristic polynomial is the same. Let's look at a proof of this. So what is the characteristic polynomial of A? The characteristic, let f of lambda be the characteristic polynomial of A. This is equal to determinant of A minus lambda I. This is what the characteristic polynomial of A is. Let's observe what it means for B to be similar. B is similar to A. This implies that there exists some Q such that B is equal to QA Q inverse, some invertible matrix Q such that B is equal to QA Q inverse. And what is the characteristic polynomial of B? It is the determinant of B minus lambda I. So let's explore what is this. Then determinant of B minus lambda I in particular is the determinant of the matrix QA Q inverse minus lambda I. But notice that lambda I is just a scalar multiple of the identity. In particular, you should sit down and check that it commutes with every matrix. So this is nothing but determinant of QA Q inverse minus lambda I into Q inverse, because Q inverse is just the identity, and because it commutes, this will just turn out to be QA Q inverse minus Q lambda I Q inverse. That's good, because now we can write this as determinant of Q times A minus lambda I times Q inverse. And what do we now know about the determinant? Determinant is that special function which, when you apply to a product of matrices, will be the product of the determinant. So this is determinant of Q, determinant of A minus lambda I, determinant of Q inverse. But then these are real numbers. This is just determinant of Q times determinant of Q inverse times the determinant of A minus lambda I. And again, this is just now, this is just the product of all these terms. This is the determinant of q inverse times a minus lambda I, which is the same as determinant of a minus lambda I. So one question you might be wondering about is, why did we not write this is equal to this directly? Because we do not know how a minus lambda I looks like. Based on the complexity of how a is, a minus lambda I need not commute with q or q inverse. So we cannot directly write the red equality which has been just pointed out. So we have to go through this roundabout way to finally get to this. And this is the final thing that we wrote is nothing but f of lambda, which is the determinant of a minus lambda I, which is the determinant, which is the characteristic polynomial of a. So yes, so the characteristic polynomial, hence characteristic polynomial of b is equal to f of lambda, which is the characteristic polynomial of a, and we have proved the result. Okay, so let's go back to the statement once more and try to see the implications of this. What this tells us is that if two different matrices are similar, the characteristic polynomial is the same. Now, if you take a linear operator T on a vector space V and you look at a basis beta, then the matrix of T with respect to beta, so T beta beta, this is an n cross n matrix, let's call it A, and let's pick another basis beta prime, and you look at T beta prime, let's call it B. From one of the theorems which we proved in the last week, we know that A and B are similar. That exists some matrix Q such that B is equal to QA Q inverse. And what this proposition tells us is that the characteristic polynomial of A and B is equal, is the same. So in other words, this enables us to talk about the characteristic polynomial of the linear operator T. So for all practical purposes, studying characteristic polynomials of n cross n matrices gives us all the information and necessary tools to talk about the characteristic polynomial of a linear operator, which is now well defined. All right, let me not go into that and spend any more time. Let's continue with the analysis and study of the characteristic polynomial of a given matrix. Okay, so before we jump into any more properties, let us notice what we are doing when we are computing the characteristic polynomial. So notice that f of lambda is just the determinant of a11 minus lambda a12 up to a1n, an1, an2, ann minus lambda. So this you can think of now as the determinant of a matrix which has polynomial entries, polynomials in lambda, indeterminate being lambda. So the next proposition tells us that if we look at the determinant of such a polynomial with entries in P1 of R, so notice that all of these a11 minus lambda up to ann minus lambda, all these are polynomial entries with degree less than or equal to 1. So the constants have degree 0 and the non-constant polynomials have degree 1. So this is a polynomial with entries in P1 of R. The next proposition tells us that the determinant of such a matrix, we will be able to say something about the degree as well. So let me write down the proposition and then tell you the conclusion. So let A be an n cross n matrix with entries in P1 of R. So like in the case when we computed the characteristic polynomial, A minus lambda I, for example, is one such example when our A was the, not this particular A, some other A. or maybe I should just call it B, or let it be A, B, maybe I'll call it B. So let B be an n cross n matrix with entries in P1 of R. Now the situation fits. So look at one of the A's which we considered earlier, and we look at A minus lambda I. A minus lambda I equal to B is a perfect example for a matrix, n cross n matrix with entries in P1 of R. The conclusion of the proposition is that then determinant of B is a polynomial of degree less than or equal to n, i.e. dit B is in Pn of R. That's quite nice, because if we manage to prove this proposition, what we have essentially proved is that the characteristic polynomial of a given matrix A is a polynomial of degree less than or equal to n. So let's look at a proof of this proposition. Proof. The proof is by induction. So let's start the induction by looking at n equal to 1. So for n equal to 1, what will our B be? B will be just a 1 cross 1 matrix. So it will look like A lambda plus B, right? Small a lambda plus small b. And what is determinant of B? Determinant of B is just going to be the exact same entry, which is A lambda plus B, which in particular is in P1 of R. So that's what we had Pn of R here, because n is equal to 1, which is equal to, let me write it in brackets, P1 of R. So yes, so the n equal to 1 case is easily getting satisfied. Now let's assume the strong induction hypothesis. Assume that the result has been established for up to n minus 1. So we would like to now take the case when A is an n cross n matrix and then prove the result. Okay, so how about jumping into that? So let us look at the, so let's call the matrix B to be, did I call it B while starting off? Yes. So let B be something like B11, B12, B1n, Bn1 to Bnn. Notice that now each of these Bij's are in P1 of R. So they are polynomials of degree less than or equal to 1. Now let's look at the cofactor expansion to calculate the degree of B, the determinant of B. So the cofactor expansion of B can be written in the following manner. Then determinant of B will just turn out to be equal to B11 times, let me put it like this, determinant of B11 tilde minus B12 times determinant of B12 tilde, and so on. Maybe I'll write the last term, minus 1 to the power n plus 1 times determinant of B1n tilde. Now notice that B1j tilde, this is an n minus 1 cross n minus 1 matrix. What was B11 tilde, for example? B11 tilde was the matrix obtained by deleting the first row and the first column. B12 tilde was the matrix obtained by deleting the first row and the second column, and so on. So they are all B1j tilde is an n minus 1 cross n minus 1 matrix with entries in P1 of R. So remember that all the entries are degree less than or equal to degree 1 polynomials, entries in P1 of R. And now the induction hypothesis is in force. By induction, because this is n minus 1 cross n minus 1, by induction, determinant of b1j tilde is an n minus is a polynomial of degree at most n minus 1. It is in Pn minus 1 of R. That implies that B1j times the determinant of B1j tilde, this is a polynomial of degree at most n. Why is that the case? Because B1j has degree at most 1. Determinant of B1j tilde, that has degree at most n minus 1. Product of the two polynomials will have the sum of the degrees of the two polynomials. So, it will be at most n. And Pn of R is a vector space. So, if you add polynomials of degree less than or equal to n, we have a polynomial of degree less than or equal to n. Hence, their sum is a polynomial of degree less than or equal to n. Therefore, determinant of B is in Pn of R. So, we have established the result. So, as a corollary, immediate corollary is that let A be an n cross n matrix in R, let A be an n cross n matrix with real entries then the characteristic polynomial of A, this is a polynomial of degree at most n, is a polynomial of degree at most n. Okay, so that is some advancement. However, I would say that we are not good enough yet to study the characteristic polynomials, because it's just saying it is at most n. So, the question naturally comes up, is the characteristic polynomial having degree equal to n, or does it have degree less than n? So, we will take the study a bit further, and we will in fact say that it has some nice form, which is captured in the next proposition. So, let A be the matrix A11 to A1n, AN1 to ANN, matrix n cross n matrix with real entries. Then the characteristic polynomial of A, it has a particularly nice form. Polynomial of A is given by f of lambda, which is equal to a11 minus lambda into a22 minus lambda, the product up to ann minus lambda plus g of lambda. So, notice that I am again treating it as a polynomial in the indeterminate lambda. And what is g of lambda? Where g of lambda is a polynomial of degree at most n minus 2. So, the proposition actually is saying that f, the characteristic polynomial of A, necessarily has degree n, because g of lambda, if you notice, has degree less than less than or equal to n minus 2, and a11 minus lambda into a22 minus lambda up to ann minus lambda is necessarily a polynomial of degree n. So, this indeed answers the question I just asked. Is the characteristic polynomial of degree n, or is it less than n? It is equal to n. So, let us give a proof of this. The proof will again be by induction. So we'll prove this result. Oh yes, so I think I should put one condition here. Let n be greater than or equal to 2. We need at least n equal to 2 to say something like that. Otherwise, the notion for g of lambda doesn't make sense. Right. So n greater than or equal to 2, this particular statement is true. So we'll prove the result by induction. So to start off, the kickstart the induction, let's consider the case when n is equal to 2. So when n is equal to 2, what is our A? A is just going to be A11, A12, A21, A22. And what is our f of lambda? That is just going to be A11 minus lambda into A22 minus lambda minus A12 times A21. Well, that is good. This is exactly what we were trying to establish. Notice that minus of A12, A21, this is a polynomial of degree 0. It's a polynomial of degree 0, which is 2 minus 2. So yeah, it is in Pn minus 2 of R. So yes, so the induction hypothesis does start with n is equal to 2. Let us assume that it is satisfied for up to n minus 1, and we will prove that for n the result is true. So assume that the result is proved, result is true up to n minus 1. Now let's look at the matrix A, which is an n cross n matrix, where the entries are given by say A11 up to A1n, an1 up to ann. What will be the characteristic polynomial f of lambda? That is just going to be determinant of the matrix A11 minus lambda, A22 minus lambda. Along the diagonal, I am writing the entries first. The remaining terms are as usual. Alright, so this is exactly what our f of lambda is. Now let's look at the cofactor expansion along the first row. What will the cofactor expansion be? It will be A11 minus lambda times, so this is the cofactor expansion of the determinant, times the determinant of the matrix A22 minus lambda, an1, ann minus lambda, a2n. Right, that will be the first term. What will be the second term? The second term will be minus of a12 times, so let me just write it as b12 tilde, determinant of b1 or determinant of let me write it as b12 tilde, where b12 tilde is, if you call this matrix equal to b, this is the relevant minor, and so on. Okay, let me write down the final term. This is just minus 1 to the power n plus 1 determinant of b1n tilde. Alright, so this is the cofactor expansion of the determinant of B, where B is the matrix A minus lambda I. Okay, so what is the first term? Let's go one after the other. Let's focus on the first term. The first term, if you notice, this is A11 minus lambda into the determinant of A, let's put it this way, A11 tilde minus lambda I, where A11 tilde is the matrix obtained by removing the first row and the first column of A. So A11 tilde minus lambda I n minus 1 in this case. So now this is just the characteristic polynomial of the matrix A11 tilde, and the induction hypothesis kicks in. We will be able to conclude that this is equal to A11 minus lambda into, let's call it F, well, it will be F A11 tilde of lambda plus G11 of lambda by the induction hypothesis, where this is of degree n minus 1. Oh, no, in fact we can say a lot more. This will, by induction hypothesis, this will turn out to be a 2 minus lambda into a 3 minus lambda up to a n minus lambda plus g, well, let's put it g11 tilde. So notice that what was our statement? The statement was, I'm underlining it in green, the characteristic polynomial has this particular type, right? This is the form of the characteristic polynomial of A. In our case, our A now is A11 tilde, which is the matrix with diagonal A22, A33, A up to ANN. This is exactly what it will turn out to be. Well, this is equal to A11 minus lambda, A22 minus lambda plus up to ANN minus lambda plus A11 minus lambda into G11 tilde. Okay, what was G11 tilde? Where G11 tilde was some polynomial in Pn minus 1 minus 2, which is Pn minus 3 of R. So it's a polynomial of degree less than or equal to n minus 3, a polynomial in lambda. If you multiply it to a degree 1 polynomial, so this will just turn out to be equal to, let me just write it as G11, where G11 is A11 minus lambda into G11 tilde, which is now in Pn minus 2 of R. So the first expression here, which I am underlining now in, well, let me see where it is, which I am underlining now in green, this is going to look like this. Now let's focus on the next term, which is being underlined in red. Now if you notice carefully, what is this? This is A12 times determinant of B12 tilde, but this is equal to A12 times the determinant of, what is B12 tilde? It is the matrix obtained by removing the first row and the second column. So this is just going to be equal to A21, A to the second column is removed, first row and the second column. So A23 up to A2n. A31, the second column is removed, A33 minus lambda, A3n. AN1 up to ANN minus lambda. This is exactly what B12 tilde will be like. Now look at the determinant of this matrix by looking at the cofactor expansion along the first column here. First column of this matrix, the matrix which I have just put in the box. What will it be? This will be some A11 into A21 times some matrix which is an n minus, let's see, this is an n minus 1 cross n minus 1 matrix. So this is going to be an n minus 2 cross n minus 2 matrix. Then there will be a minus A23 times the determinant of something. So let me be precise. This is A21 times determinant of a matrix. Similarly, this will be A23 times determinant of another matrix n minus 2 cross n minus 2. The terms I will not write because they are not important. The thing to notice is that by the previous proposition that we proved, this determinant will again turn out to be a polynomial of degree less than or equal to n minus 2. So this is going to be A11 into A21 times some polynomial in Pn minus 2 of R plus, or rather minus, A23 times a polynomial in Pn minus 2 of R. That's what matters, and so on. Everything will be like that. And notice A11, A2 and all these are constants, or rather scalars, real numbers, degree 0 polynomial. So this will just turn out to be some G22 which is in Pn minus 2 of R. So this red will just turn out to be this red, and this is exactly what this red turns out to be. Now I will not go about with the remaining terms. The remaining terms are proved exactly similarly to be in Pn minus 2 of R. The only thing to note is that when you are now considering the term corresponding to A13, you should expand the determinant of the matrix corresponding to whatever is being noted here. You should expand that along the third row. So the nth term should be expanded. The cofactor expansion should be along the nth row. And at every stage, we will end up with a polynomial of degree less than or equal to n minus 2. So finally, what do we have? The green thing that I have just written down plus many polynomials of degree less than or equal to n minus 2. So hence, our f of lambda is just going to be a11 minus lambda into a22 minus lambda up to ann minus lambda plus there was a g11 plus g12 plus up to g1n, where each of these gij's are polynomials of degree less than or equal to n minus 2. Hence, f of lambda is equal to a11 minus lambda. The sum of such polynomials g11, g12 up to g1n will all turn out to be again a polynomial of degree less than n minus 2. So where g is a polynomial of in Pn minus 2 of R. With this, we have established our result. So notice that that's precisely what we wanted to prove. Where is it? Here, f of lambda. I'm putting it in box. This is exactly what we wanted to establish. We have done that. In fact, we can say a little more. If you notice, our f, so let's keep it here for immediate reference. F of lambda is, what is it? If you expand out a11 minus lambda plus up to ann minus lambda, this is just going to be equal to minus of 1 to the power n times lambda to the power n plus minus of 1 to the power n minus 1 times a11 plus up to ann times lambda to the power n minus 1 plus a degree 2 polynomial. And what is a11 plus a22 up to ann? This is nothing but the trace of the matrix A. So that's good. So suppose, in fact, the remaining terms, if I have to write it out something as a2 lambda to the power an minus 2, let me start from that, n minus 2 lambda to the power n minus 2 plus up to a0. Suppose this is our f of lambda. Okay, so what is f of 0? F of 0 is just going to be equal to a0. So that means we know what a0 is if we can get hold of what f of 0 is. But what is f of 0? F of 0 is the determinant of a minus lambda is 0. So lambda 0 times I is just going to be determinant of a. So we know what a0 is. A0 is the determinant of a. So let me just write it down as a theorem. So all the effort we have just spent can be captured in the following theorem. So let A be an n cross n matrix. So let n be greater than or equal to 2. and AB an n cross n matrix given by, well, let's not bother about what the form is. Then the characteristic polynomial of A is given by f of lambda is equal to minus 1 to the power n lambda to the power n plus minus 1 to the power n minus 1 times the trace of A into lambda to the power n minus 1 plus dot 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 plus finally the determinant of A. So the characteristic polynomial encodes in its coefficients the trace and the determinant of our given matrix A. So we have concluded something substantial by studying the characteristic polynomial of a given matrix, and we now know how well the characteristic polynomial looks. So this is actually quite nice. If you look at 2 cross 2 matrix, this is quite straightforward. For example, if A is say A11, A12, A22, A21 and A22, what is going to be f of lambda? F of lambda will, let's compute it and see. A11 minus lambda into A22 minus lambda minus A12 times A21, which is equal to minus lambda square minus A11 plus A22 times lambda plus A11 A22 minus A12 A21, which if you notice, this is equal to lambda square minus the trace of A times lambda plus the determinant of A, which is nice. Well, let's look at what happens when A is a diagonal matrix. So let be equal to A11, 0, 0. Another case which can be easily checked. Then f of lambda, this is just A11 minus lambda up to ANN minus lambda, which we have already noticed is minus 1 to the power n times lambda to the power n plus minus 1 to the power n times A11 plus up to ANN times lambda to the power n minus 1, so this is n minus 1, plus the constant term here is very clear. It will be A11, A22 up to ANN, which is exactly the determinant of the matrix A. Okay, so let's now analyze this f of lambda a bit further. So notice that f of lambda is a polynomial of degree n. Okay, so since f of lambda is a polynomial of degree n, it is possible that we can write it as a product of n factors. So it could possibly factor into n linear terms. Let me note that down. Since f of lambda is a polynomial of degree n, it might be possible to write f of lambda as a product of linear factors. Not necessarily always possible when we are considering matrices with entries in real numbers, but maybe sometimes it is possible. So i.e., we might be able to write f of lambda as the minus 1 to the power n term will be, say, coming out, and it could possibly look like minus 1 to the power n times lambda minus lambda 1 into up to lambda minus lambda n. Not necessary that these lambda i's are distinct. Such a restriction is not being imposed, but it might be possible to write it like this. In such a case, we say that the polynomial f splits. So let's look at a couple of examples, and a couple of examples where it does split and when it doesn't split. So let's look at the simplest examples. For example, let a be equal to 1, 0, 0, 1. What is going to be f of lambda? F of lambda just will be lambda 1 minus lambda minus 1 the whole square, the identity. So let me put it like this: I 1, 0, 0, 1, it's just going to be lambda minus 1 the whole square, which is lambda minus 1 into lambda minus 1. In this case, it does split. How about when a is, say, 0, 1, 1, 0? Then f of lambda will be lambda square minus 1, which will be lambda plus, maybe I'll put it like this, lambda minus 1 times lambda minus 1. Yet again, it splits. Let me not give you the impression that it always splits. Just tweak the above example 0, 1, minus 1, 0. Then f of lambda will just turn out to be equal to lambda square plus 1. We know that this is actually lambda plus I into lambda minus I, where I is the square root of minus 1, but over the field of scalars being real numbers, this particular polynomial does not split. We will also, let's look at another simple example, the play with zeros and ones. What will f of lambda be here? F of lambda is lambda square, and notice that this is lambda minus 0 into lambda minus 0. So again, it splits. So there are cases when it splits and there are cases when it doesn't split. So what can we say about when our given matrix A is a diagonal matrix? That's the case when it is quite interesting. So if A is something like, say, A11, 0, 0, A22, 0, and so on, we know exactly what the characteristic polynomial of A is. Here, f of lambda is just equal to, I'll write it like this, minus 1 to the power n times lambda minus A11 into lambda minus A22 up to lambda minus ANN. So in the case of a diagonal matrix, we know that the characteristic polynomial necessarily splits. And we also know that if a matrix is diagonalizable, that means that it is similar to a diagonal matrix. And we just proved in the beginning of this video that similar matrices have the same diagonal, and therefore the similar matrices have the same characteristic polynomial, and therefore the characteristic polynomial of a diagonalizable matrix necessarily splits. So notice, so I'll write down as a lemma, which I will not prove, I just said it in words. The characteristic polynomial of a diagonalizable matrix necessarily splits. So in other words, if we get hold of a matrix whose characteristic polynomial does not split, then that matrix is not diagonalizable. So in particular, let's come back to this example. In this particular case, which I am now putting in red, the characteristic polynomial does not split. So we know for a fact that A is not a diagonalizable matrix. So this is one easy way of checking for whether a given matrix is diagonalizable. But of course, characteristic polynomial is something which we have to compute to do that. But nevertheless, once it is computed, if it's easily seen that it does not split, you can conclude that it is not diagonalizable. So this is a necessary condition. So the question now pops up is the following: if you have a matrix whose characteristic polynomial splits, can we conclude that the given matrix is a diagonalizable matrix? So that, in other words, is the condition that the characteristic polynomial splits. Is this a sufficient condition as well? So I will not keep you in suspense and say that it is not necessarily the case. That's not a sufficient condition. However, the splitting of the characteristic polynomial can be studied in depth in order to conclude something about the diagonalizability of the given matrix, which will be the content of the lectures to follow.